Welcome everybody to another fun and exciting day of Computer Science 101. Um, hope you're all having a good Wednesday. Let me get rid of Discord. We don't need that here. Um, so um, had a couple of requests to talk a little bit more about the Python stuff, so I thought I would do that. And in particular, I kind of want to walk through the algorithm a little bit more. I kind of did that quickly at the end last time, um, and but I want to make sure that it's the algorithm itself is kind of clear. So let me actually blow this up so it's a little bit more readable. Um, okay, so let me start with the sort of standard, the subtraction only version of the algorithm because it's the simplest of the algorithms. Okay, so for the purposes, so the project, right? I've given you guys basically some program, or say with task 3 and 4. Maybe I should be a little bit more clear. With task 3 and 4, I've given you the algorithm. I've written it in Python, um, and the and yes, this is basically we're not going to have a final exam. We're just going to have this last project. And sorry, I'm looking at the Discord. I mean the stream chat. Yeah, so I was originally planning to have this due next week, and then we would have a traditional final exam. The timing and stuff has just not worked. We've been moving a little slower um, than ideal. So yeah, so we won't have a final exam, but we this project is basically just going to it won't take the place of the final in terms of grading. So what I did was I took the percentage that the final would have been and just redistributed that to the other parts of the course grades. So um, anyway, so this project will be due at the time that the final would have been. Um, but yeah. So anyway, it seems from the Twitch chat that this is a very unpopular idea. In particular, Reese seems to be very displeased about there not being a final. So Reese, I can write you a special final if you'd like. That only you have to do. How's that sound? No. Okay. Well, anyway. All right. So, um, yeah, I didn't figure there would be much complaints about this. Um, all right. So anyway, um, great. So yeah, so tasks 3 and 4 are basically to translate a program in Python into the assembly for our processor. Tasks 1 and 2, you do not have Python to start with, but the algorithms are relatively short, so you'll be able to figure those out on your own. So a couple of things about Python here that we need to make sure that we're clear on. So um, the these first two statements, OG num A and OG num B is 58 and 87. Um, can you exercise the senior option for the last project then? Um, yes, you can. And in fact, I'm even nicer than that because I offer a freshman option, a sophomore option, a junior option, and a senior option. It's like on Oprah Winfrey, right? You get an option, and you get an option. Everybody gets an option. The option is you do the project or you get a zero. So, um, yeah. Anyway, um, so right. Okay. So, the back to what I was uh, Oh, yeah. So, yeah, Teague, there is no super senior option. Because yeah, I want you to graduate and go away from this place. So, no, Mia, I'm teaching right now. Thank you. Um, okay, sorry, my dog was getting ornery. Okay, so this program requires there to be two numbers that we're going to compute the GCD of. Okay. Um, and so I had to pick two numbers for sake of example. And in the code here, I just put 58 and 87 and I basically pick those at random. Okay. And then I have two other numbers, which I've called num-A and num-B, that initially start as being the original numbers. And the reason I made sort of two copies of both numbers is that the OG num A and num B will never change. So I will always have away from your face. Like, is that better? Um, oh, I see. My beard is hitting my mic. Yeah, well, this has been maybe a good reason to not have a beard. Um, no, Mia, I'm teaching, dog. Um, Okay, so num A and num B will change over time, but the OG copies of them do not. Um, and that uh, basically just means that I have stored a copy of the two numbers to begin with. Now, for the purposes of your program, you're going to be loading the first or the two numbers from memory cells. I think I said E0 and E1, and so these two things are just going to be in memory, and then num A and num B will be when you load them into registers. And the values in the registers will change, but the values that are sitting out in memory will not change. So, okay. No, dog. Come on. Come on. Okay. So, now, what's the algorithm? So, um, the first thing is if one of the numbers is 0, then um, the the convention is that if you have one of the numbers equal 0, then the GCD of the two numbers is just defined to be 0. Okay, and that may seem a little silly, but that's sort of the convention from number theory. And so that's this very big thing here at the beginning, which is just let's check to see if either number is 0, and if so, then if so, then we just return the answer 0 and we quit. The other thing would be if, and you can assume this for the sake of your program, although we could certainly write a little snippet at the beginning, which is you can assume that the two numbers that you're starting with are not negative numbers. Um, if one of them was negative, so like let's say that I was trying to find the GCD of negative 58 and 87, then um, the way I would do that is just, well, the GCD of negative 58 and 87 is going to be the same as 58 and 87 because the sign doesn't change the divisibility. Um, but for our sake, we'll just assume that that's not an issue, um, that the numbers you start with are both uh, either 0 or positive. Okay, and the other thing I want to make sure that's clear here, just for sake of example, is the 58 and the 87 here that I've typed, those are not in hex, those are base 10 numbers. And if you wanted the number 87 in hex, whatever it is, um, then or 5/8 in hex, then that's something different. Okay. So if I were to program this particular 58 and 87, I would need to figure out what 58 is as a hexadecimal number, and similarly with 87 to program to put those into memory. So okay. And I'm about to kick the dog out of the room. No, Mia, you're getting kicked out. Oh, the joys of a wireless microphone. So, okay. Sorry about that. Okay, so then how does the algorithm work? Um, the If the two numbers are zero, or one of the two numbers is zero, then you just output the answer being zero, and that's the end of it. If they're not, if both of them are not zero, okay, then we go into this loop, and what we're going to do is do this continual subtraction business. Okay, now for the purposes of translating into assembly, there is no equivalent to the print command in our assembly language. Okay, there's no way to do that. The only things that you can do for output of numbers is basically to put them into memory someplace. Um, or just leave them in registers, because on the simulator, we can certainly see what the register's values are. So those two print commands really won't do anything. Okay, there's no translation for them in assembly, or at least not our assembly. Okay, then we have the uh, the if-then conditionals. Basically, we need to know which of the two numbers is um, smaller than the other. Okay, and we know that the two numbers are different because if they were the same, then this while loop would terminate and the program would be done. So if the two numbers happen to be the same, then their common value is the GCD, and that's the end of it. Okay. If that's not the case, though, when they're different, we're going to go into this sort of repeated subtraction part of the program, which is here. Okay. And we don't know which of the two numbers is bigger or smaller. Okay. And so there's two possibilities. Either num A is bigger than num B, or it's less than num B. And if it's less, then we'll subtract it from num B, and otherwise we'll do the subtraction in the other order, always replacing the bigger number with the difference. Okay? And then we'll continue this process on it will terminate only when the two numbers are now equal. And once they hit the um, uh, once num A and num B become the same thing, then that common value is going to be the GCD. Okay, so so let me open back up the Python terminal, um, and let's see, where did I put this? Sorry, I should have opened this up earlier. Okay, so this one, binary GCD2, and I'm sorry that the text is really small. Let me see if I can blow that up um, so that it's a little bit more readable. Oh, here we go. Okay. Um, okay, that's hopefully a little bit more readable. Um, oh, yeah, Filippo. So that's a background. Actually, let me just show it to you guys. This is a background wallpaper from the game Anno 1800, which I've been playing quite a bit of lately. Um, so anyway, um, yeah, okay, so back to here. Okay, so that hopefully is a little bit more readable. Um, and I changed the numbers to 1832 and 2020 just for the sake of demonstration. Let me change them back to 58 and 87, um, which is what I had a minute ago. And see, save that. and then let's run it. Okay, so when I run it, I'm going to get this as my output. So initially, the two numbers are 58 and 87. Okay, and I just wrote the program to basically parrot that out. Um, Steam, ha. What do you have against Steam? Um, I've been playing. Well, okay, Filippo. Let me just put you in your place for a moment. That's my Steam library. So you can just yeah. So anyway, um, okay. So 58 and 87. Um, yeah, I don't know. I mean, 420 was a couple days ago, Filippo, but yeah, maybe he's still riding high, so to speak, from then. All right, so 58 and 87 were the two numbers I picked. 58 is smaller than 87, so I'm going to subtract 58 and 87 and replace 87 with that difference. 58 and 87 happens to be 29. Okay, so then the 87 got replaced with 29. The two numbers are now still different, and so I would subtract 58, or sorry, subtract the 29 from the 58, and that difference happens also to be 29. Now my two numbers are the same, and so my GCD is 29, the common difference. So in this particular case, it only took basically um, two steps for the algorithm to complete, and um, if I change the numbers, so let me go back to what was it? I had 1832 and 2020. Um, so let's run that one. Okay, then here's the sequences of numbers that we would get, right? So we start with 1832 and 2020. 2020 is bigger, so we subtract and replace 2020 with 2020 minus 1832, and that gets us this pair of numbers. And then, as you can see, I mean, I won't read through all of them. The pattern continues, and eventually we get down to the point of the GCD being 4. Okay. Uh, Now, this version of the algorithm is, as you can see, not optimal in terms of efficiency because it took, looks like 10 or 20 steps. It took a whole lot of steps in here to run through it, but it will eventually terminate, assuming everything is programmed right, and you will get the correct answer. Okay, so there we go. Now, back to the algorithm. So let me put that here. Or actually, why don't we move to talking about the tasks? Okay. So the first two tasks are relatively short. Okay. And um, the first task is how can you tell whether or not a number is odd or even? So we wrote a sample program that's in the notes that determines whether or not a number is positive or negative. Okay, and we figured out a technique for doing that. Um, Basically, what did it come down to? What was the big idea? How do you know, just looking at a number, if it's positive or negative? What's the technique? Yeah, okay, you look at the far left bit, the most significant bit, and if it's a 1, then your number is negative, and if it's a 0, then it's not. Okay, and so we used a masking technique in order to extract out that information, and because we didn't care about the other 7 bits, we only cared about the 8th one. Um, so, right. Okay, so how do you tell if a number is odd or even? An integer is odd or even. Okay, so sort of similar idea. Which bit do we look at to tell us whether or not we've got an odd or an even number? Yeah, it's the far right bit, okay? And because in binary, right, the bit positions starting from the right are 1, 2, 4, 8, 16, and so on. Well, notice that 2, 4, 8, 16, etc., those are all even numbers, okay? So the only way you can get an odd number is to have a 1 at the final end in the ones place. Okay, if you have a 1 in the ones place, then your number is odd, and if you don't, if you had a 0 there, then your number is even. End of story. Okay, so task 1 will look a lot like our sample program to determine whether or not a number was positive or negative, but instead of looking at the far left bit, this time we're looking at the far right bit. Okay, so a little different, but not too much different. Okay, the second task is, so if we look back at our algorithm here, um, notice that one of the key things that we needed to know was whether or not a number is smaller than another number, okay? And the way that we can test that is let's subtract one of them from the other, and if the difference is positive, then um, uh, then the bigger number was the one that we subtracted from. Otherwise, it was the smaller number, right? So the way to do, or the way to think about this is, so I've got, let's take this inequality here. The number A is bigger than the number B precisely when A minus B is bigger than 0. Okay, and if the inequality goes the other way, then this inequality goes the other way. Okay, so determining if one number is bigger than another is effectively the same as determining whether or not the difference is positive or not. Well, we know how to compute the difference. Okay, we know how to do this two's complement stuff, and task, not task 1, but the example program um, determines whether or not a number is positive or negative. Okay, so this basically is to take the positive and negative program and essentially add on a little bit to it. So we wrote really here two programs examples. We wrote a program that did subtraction. We wrote another program that determined if a number was positive or not. And by combining the two, that will get us the thing in task 2. Okay, now task 3 is to take this algorithm here that I've got on the right, okay, sort of the subtraction only version of the GCD algorithm, and to translate that into assembly and then therefore machine code. Um, so here you have the algorithm, okay, you've got basically everything, the pseudo code, if you will, written in Python, and um, so what you want to do is translate that into assembly. Now, you will definitely use task 2 in doing so because task 2 was sort of the part of the program that dealt with how to determine which of the two numbers is bigger, and that you need basically right here because you need to know whether or not you're doing the if case or the else case. Okay. All right. Now, task 4 is the hard one um, because the algorithm is more complicated. And let me go to the code for that. It's either this version here or this version here. In fact, let me actually open. I think I called this one binary GCD 3 no steps. Yeah, this one. Okay. And for sake of example, let's take 1832 and 2020, and let's compare the output. So if I run this one, it took, basically a full monitor length worth of steps in order to get the answer. Okay. And if I run this version, it only took that many steps to do it. Because basically what I was doing is anytime I have an even number, so for example, in this case, 1832 and 2020 are both even, so I know that 2 is one of the factors of the GCD. I can divide both of those by 2 immediately and keep track of the fact that I did so. And because I'm doing division by 2, my numbers drop in size much more quickly until I get down to the point where um, the numbers are nice and small. And I am not sure. I think I might have a little bit of a bug here because it didn't display the GCD. Um, I'm not sure why it did that. It should have printed the GCD here at the end. Um, oh, I'm sorry. I'm looking at the wrong program. We wanted this one here. Uh, well, I may not. Okay. Let me rerun that. Looks like I may have a little bit of a bug in here. Um, okay. Let me open a the other version of it. I was tinkering with this the other day to try and clean up the code a little bit, and I may have accidentally messed something up. Yeah, it looks like I messed something up. Um, okay, well, I'll figure out what I messed up. It's probably something kind of silly. Um, so, yeah, I'll figure that out. So anyway, my point though was that the we get down to this point here, and our it should have spit out our GCD, but it took way fewer steps to do it, um, and um, yeah. Oh, I think I see what the problem is. It's because I'm doing the shifts here. Um, yeah. Okay, actually, you know what? Let me open up. Oops, I did not mean to quit that. Let me open up the one that's slightly simpler. Um, we open up. Oh, and of course, now I have to go find the bloody file. Okay, sorry about this, guys. Let's see. Wabash teaching CSC101. This would have been the file I wrote last semester. Oops. And this one. Okay. This is the one I wanted. All right. There we go. Okay. So, yeah, anyway, here's the sequence that we get. It turns out that this one takes 23 steps. Um, it doesn't look like it's 23 steps, but basically what I did was every time that I did a division by um, time I had a division by 2, I increased the number of the steps, but I didn't actually print out the numbers that way. So there's more steps than actually are printed. And Reese, the I did multiply it back in, but so let me here, this is what it is. So I think the issue is right there, that what I was doing was saying, okay, well, if the two numbers are odd, then I know their difference is even, and so I can pull out a factor of 2 immediately. Um, and but the problem is that then I'm dividing them by 2 without first checking are they the same. And so really I needed to get rid of this thing here. Um, so yeah, so compare that to here where I'm not dividing by 2 in the subtraction bit. Um, the multiplying it back in is this line right there. The answer equals num a left shift. Um, so if I divide by 2, that's equivalent to right shifting the bits. If I want to multiply by 2, then that's equivalent to left shifting the bits. And so the multiplying it back in is accomplished by this little bit here. So if let's say that I shifted right 4 times, then that means that I've divided by 2 4 different times. And in order to put that back in, I need to multiply by 2 4 different times, and that's equivalent to left shifting instead of right shifting. So, okay. All right, so anyway, the point I wanted to illustrate though is that while the program is a little bit more sophisticated looking, because we have sort of this addition here, um, um, which is basically saying, is the number even? If it's an even number, then you can keep dividing it by 2 until you get an odd number. And this bit at the very beginning is to say, okay, if the two numbers you start with are both even, then you can pop a factor of 2 out of it immediately and keep doing that until you have the situation where both of neither, sorry, where at least one number is odd, and then you can move on to the rest of the bit. So I could probably rewrite this a little bit to make it even more efficient or more clever or something, but this is maybe um, good enough for uh, sake of example. The other thing here that we wouldn't necessarily have in our assembly is, I mean, you could put it in if you wanted, is the step counter, which basically just starts at 0 because you haven't done anything yet, and every time you do an operation, then I increased the step counter by 1. And I really probably should have increased it by 2 in this case because we did 2 different divisions, but whatever. Um, Basically, just to keep track of how many steps the algorithm took. Um, and that's not necessary for in terms of the actual computation, but it's maybe interesting information to kind of know how long it took for these particular algorithms to run, um, how many steps. So, okay, now, um, so I want to be clear on something that I did get a couple of questions about. So, namely, you guys are not going to write Python code for the project, right? So, what you guys are going to write is assembly and then also machine code. And let's make sure that we're clear on the difference there. Let me go to, okay, so this, what's highlighted is assembly, okay? It's still somewhat human readable. It's not as human readable as, say, Python, but it's a lot more human readable than this, which is the actual machine code. Okay, so the load 1 comma $E0, that sort of stuff, the the load thing here in the third column and the fourth column, those guys collectively are the assembly, and then the machine code is when you translate it into the sequence of numbers that that identifies basically each instruction and its operands. Okay, so when I say you're going to write an assembly, you're going to produce things that look like that, and also the link, the code at the bottom, which is what takes us to the online simulator, and that's where you actually execute everything. Okay, um, so yeah. Um, okay, and let's see. I think we're good here. This line here that I put GCD really um, uh, is so Python does have a GCD algorithm built into it. Um, and so when I did this import math up at the top and then used Python's command math.gcd, that's using Python's version of the GCD algorithm. And the reason I put that in is when I was first writing this, just to make sure that that I wasn't screwing something up, I have the program tell me what it thinks the GCD is, and then I have Python use its built-in program that knows how to do GCDs. And obviously, I want the two answers; they ought to be the same. Um, so Teague asked about the assembly. You really only need to write for the assembly the last two columns. So basically, assembly is going to be two columns: the mnemonic, which would be like load, move, jump, etc., and also the second column, which has got your operands and stuff. That, strictly speaking, is assembly. Now, as I think you guys saw when we wrote this particular program, it was useful for us to have the memory addresses down the left and the translate each individual instruction into its corresponding opcodes also there. Because then I could just go through and copy that second column to produce my bytecode for the simulator. Um, so yeah, so you don't have to do that, although I think you guys will find that having the memory addresses and the opcodes there when you're finished with the program is just kind of convenient. Um, yeah, so some assemblers. So for example, let me go to uh, the 8-bit workshop that I think I showed you guys earlier. Okay, so um, let me go to let's do Game Consoles NES, and let me do an assembly example. Okay, so um, Atom is not really configured for this kind of view of it, but one of the things that's pretty nice about uh, uh, some IDEs is they give you line numbers down the left, and then they also give you for each line, they give you the memory address that it's in, and then the opcodes for it. And so, for example, here, um, this particular um, uh, instruction JSR, that's kind of like our jump instruction, has the opcode 206680. And then there's another one that's clear RAM, which is 204480. Um, and the way to read that is the opcode is 20. Okay, so on our processor, the opcodes are always just 4 bits because we only have 12 operations. On this machine, there's 100 and something, and so you actually need a full 8 bits for the opcode. And so what this is 20 says it's a jump, and then the memory address we jump to is 8066, which is located further down in memory. It's not shown here. Or, for example, this one, 208044, would jump down to the instruction located at a memory address 8044, which would be sort of somewhere in here. Um, so that looks like it's written backwards, 8044, and it kind of is. For technical reasons, uh, the way that this thing loads in numbers looks a little backwards from what you would expect. So anyway, but so you've got the opcodes there, and on this processor, what's kind of interesting is not every opcode is exactly the same length. So some opcodes only take 2 bytes of memory, others take 3 bytes of memory. Just sort of depends. Here's an example. Um, of one that loads, so the A9 is the opcode that loads a register, um, and then 3F is what gets loaded into it. So the opcode is A93F, and that sits starting in memory cell 0 or 8028, and then this 2 over on the right tells you how many cycles of the processor it takes to execute that thing. And as you can see, different instructions took a different number of processor cycles to execute. I should also mention, so the memory addresses here are take 2 bytes rather than just 1 byte. And that's because the processor for the original NES and a bunch of other machines that used it um, had a 16-bit or 2-byte memory address field, and so they were able to address 64 kilobytes worth of memory, and which is a whole lot bigger than our 256 bytes. Yeah, anyway. Um, so one thing I really like about this online IDE, right, is that all you do is type things here, and then it automatically does all the stuff to the left here for you, which is kind of nice. Um, Atom doesn't have that capability. It probably does, but I would have to define what the assembly structure is and stuff. I would basically have to teach it this language, and I haven't gotten around to doing that. So, anyway, um, yeah. So, okay. Um, let's see, what else did I want to talk about today? Um, Let me go back to the project file. Um, all right, so here. I would strongly suggest working on these tasks in order because I sort of uh, put them in a certain order in order to kind of help build you up a little bit. So the first 2 tasks are not going to be too difficult. In particular, the first task will be relatively straightforward. Really, all you've got to do is adapt the example that I wrote for positive negative um, to being odd even. And as we said, the moral of the story is you look at the far right bit rather than the far left bit. Okay, great. Um, and then task 2 will be a little bit more challenging because that's where you've got to take sort of 2 examples that I've written and kind of synthesize them together. And then the meat of this is task 3 and task 4. Um, and yeah, okay. So anyway, you guys can do this, okay? Um, Let's see. Oh, the zip file thing. Yeah. Atom, you can just download it. So just Google um, for Atom text editor, And there you go. Download it. It's free. Um, and that's that. Um, and then how to make zip files. Okay, so I'll show you guys since I'm on my Windows desktop. Let me start with that. Okay, so let me go to let's see here. Okay, so I've got a bunch of files here, right? So my Python files. So if I select all of them, everything I want to zip, and then well, I thought Windows had this built in. Okay, I have a little program installed called 7-zip that will do it. I could have sworn that Windows could do it. Isn't there a compress option someplace? Um, okay, I could have sworn that Windows could do this. Just had a built-in option for it. It just shows you how much I use Windows. I basically use it for playing games, and that's it. Uh, Okay, well, so maybe I should just make instructions for this, for how to do it. It's not complicated. On a Mac, basically, you just select the files, you right-click, and then there's an option in here that says compress, and that's the end of it. Um, oh, here it is. I see. Okay, sorry, they've changed it. So you select everything, you right-click, and you say send to compressed zipped folder. Okay, and then that will make a zipped file, uh, and then you can rename it to be whatever you want. Okay, so my zip file, and this compressed file has it's basically right. So if I look at the file properties, it's a zip file. Okay, and it contains copies of everything that you choose to put into it. Um, so that's all you have to do to make it, is select the files that you want. And in y'all's case, it'll be 4 ASM files, one for each of the tasks, and then it's send to compressed folder. On a Mac, if you select these things in the Finder, then one of the options here in the list, it would say compress 4 items, because I selected 4 things, and then that would spit out a zip file in this same directory. And then what you guys are going to turn in is the zip file. So the benefit of the zip file is that you guys only have to turn in one thing, one zip file, but it has inside of it um, 4 programs, and so you only have to upload one thing, even though it contains 4, and that makes it a little easier for me to um, keep track of everybody's files. So yeah. Um, all right. So I guess why don't we go ahead and quit for today? And I guess I will talk to you guys on Friday for sure, if not a little bit sooner. So I'll go ahead and quit the stream and have a good rest of y'all.